epoxidation. We're going to take an alkene. Let's do epoxidation plus hydrolysis. I'll set up the overall reaction scheme. We're going to take an alkene. We're going to add to it, this isn't a typo, a peracid. Talk a little bit more about this function group. It's new to some of you. So we're going to take an alkene, add a peracid to it, and we're going to get what's called an epoxide. This is stable. We can actually isolate this. We can put it in a bottle on the shelf. We can't do that with 3-membered mercurium ions. We can't do that with bromonium ions. Those things are reactive intermediates, but this is quite stable. And ultimately, if we take this and treat it with acid and water, we'll end up making a trans diol. Okay, so we're going to work through this particular process. First one is reacting alkene plus peracid. We make an epoxide, then epoxides we can open with acid and water. We'll go through this now. Peracid is a combination of two function groups. This one is called carboxylic acid. This is called peroxide. So this is acid and peroxide. And notice we take OO instead of OH. We take OOH. We get this new function group called peracid. The most common example you'll see for this on standardized exams like MCAT or other exams is called MCPBA. The name isn't so important, but the structure of MCPBA is kind of a funny molecule. It's quite specific. It's a benzoic peracid, and there's a chlorine atom right here. Okay, don't need to memorize this. Key thing is, however, that we recognize this peracid function group. It's special, it's unique, and that's the key ingredient for this particular reaction. Let's actually go through this one. This is new, different, and we'll get a fresh sheet of paper for it. We're going to take cyclohexene for this one. And we're going to draw MCPBA specifically as our peracid partner. We're going to draw it right next to it in a very specific way. So this time we can't be too clumsy with it. I'd like you to try to mimic best you can the orientation of atoms, the way I've drawn this. Cyclohexene is easy, but try and draw the peracid in this kind of funky sort of horseshoe or U-shaped arrangement here. Try and draw it right next to our alkene. And I'm going to go through the mechanism, which you're not required to know. Not required to know. On our last slides, when we were talking about sodium borohydride, you are not required to know that mechanism. You should have put it in your notes. Don't study the mechanism. I'm just going to show us what the mechanism is, so we can appreciate it's quite complex. You can see that I'm a reasonable human being, that I don't need you to know all these mechanisms, but we're going to appreciate what it does, and we have to know what it makes. That's definitely key stuff, right? We have to be able to identify this as a peracid. We have to know that when it reacts with an alkene, it makes a epoxide. Mechanism starts as usual. Imagine if this is bromine bond here. We know it's a weak bond. We know oxygen's electronegative. This starts the same way. I wanted to do this in a red arrow here. Sorry about that. Come in here and do a little precise surgery with a whiteout marker. So, if this was a bromine bond, we know it's weak, and it's believed that the alkene attacks this, just like it attacks bromine. The weakest bond in this molecule breaks. These electrons get pushed in a very particular way. We now start putting a negative charge or electron density on carbon. This carbon bond breaks, picks up this hydrogen, and finally, this pair of electrons hunts out and finds the positive charge building up on this double bond. As this double bond breaks, we know positive charge is building up, and so we build, or we can quench that charge with this pair of electrons. This is really a hot mess of arrows here. I would like you to draw the product of this reaction and this, which is some alkene modified now, and then the other byproduct of this reaction, which no one cares about, especially me, is simply metachlorobenzoic acid. It's missing the oxygen here. Obviously, the alkene gets that oxygen. I want you to follow these arrows logically. I want you to break a pi bond. There won't be a pi bond in this product. There's going to be a carbon-oxygen bond for sure. This oxygen bond's broken. This oxygen pair of electrons here bonds back to carbon. What do these two arrows really mean for this particular product, right? This arrow here cuts this bond, so part of the molecule is breaking away. This particular arrow here picks up this proton, so that hydrogen atom is stuck on the carboxylic acid in the end. But right here in the middle, what happens, right? Try and follow those arrows. Draw what you think the structure of the product is. Use wedges and dashes. We have some practice in looking at something similar to this from yesterday. So please try and draw on what you think the product would be for this reaction. These little gaps of time I'm leaving you are very important. If you can do this with confidence, it means you've internalized what we did yesterday and that you understand what mechanisms are. If you're struggling, it's a point of reflection that you didn't quite get to my expectations yet. But there's still hope for you. You're young people. You're not dead yet. Just keep working and you'll get better at this stuff. What I'm hopeful here is that you drew this. The only other possible answer that would be right would be this. But this is the one that I like. These two molecules are identical, but notice that the epoxide has been formed. And if we look back and reflect on these arrows, this tells us exactly that this should be formed. Carbon-oxygen bonds being made? Check. Oxygen bond is broken? Check. Hydrogen that was attached here, it's gone, it's over here? Check. One pair of electrons from oxygen forms another bond right here. And they have to be on the same side as one another. They can't be opposite to one another. It would be impossible to put one of these up and one of these down. You can build it with a model kit to see for yourself. So this is called oxidation or epoxidation. The second step we're going to do is called hydrolysis. It's a second distinct step. So we're going to redraw our epoxide. This compound is called an epoxide. This compound is quite stable. If we put it in water, nothing happens. If we had a bromonium ion in water, bromonium ion would react immediately. If we had a mercurium ion in water, it reacts immediately. Bromonium ion, mercurium ion have a plus charge here, and these bonds become very, very weak, so water can come in and attack the backside. Epoxide plus water, nothing happens. What's the difference between this epoxide and bromonium ion and mercurium ion, besides the obvious that we're using a different atom? Let's just draw briefly an analogous bromonium ion, or an analogous mercurium ion. Three-membered ring. This plus charge makes these species very reactive. They'll react immediately with water. They react at the opposite side. It's called anti-addition. They give trans-stereochemistry. Water comes in from the back. This bond breaks. Mercury's up, water's down. It's called anti-addition, giving trans-stereochemistry. What if there was a way for us to put a plus charge on oxygen? What if we had acid, like H2SO4 or HCl, and do an acid-base reaction? This is our acid, this is our base. What if we make this oxonium ion? This is the conjugate acid of this. The conjugate base of H plus could be sulfate or chloride, just not really important for our discussion. But in this acid-base reaction, this is base, this is acid, conjugate acid. Now notice how we have a plus charge here. When these had a plus charge, they were very reactive. When this has a plus charge, it becomes very reactive. And it's going to react the exact same way bromonium ion did yesterday, or mercurium ion did about 20 minutes ago. We're going to attack at the backside. If these two positions were different, it would go for the more substituted position. So if this is a methyl group and this is hydrogen, it'd go for this side. But in this example, they're the same. So we could either come to this position from the backside, or we could have come to the other part of the epoxide since this molecule is perfectly symmetric. Carbon has 4 bonds. It doesn't want 5 bonds. So if we make a 5th bond here, the weakest bond is going to break. The weakest bond is the one that's in a 3-membered ring, which is highly strained from Bayer ring strain, which you learned about with Dr. Marinas. And there's an oxonium ion here. Oxygen wants electrons. So if we break this, we alleviate the strain, we give oxygen its electrons, and we install a new bond. The stereochemistry that takes place for this reaction? There's going to be 2 groups put in here and here. What do you think those groups are? Things that come from anti-addition give to trans stereochemistry. So the hydrogen comes up, and here we would have OH. And to get to our final product, we do an acid-base reaction. I'm not going to worry about it right now. I just want us to draw the final product here, where we have 100% trans. This is called a diol or dialcohol. So in its entirety, the slide is here for us. We'll highlight some points I want to make sure you're well aware of.